Yeah, so I enjoyed the talk so far. What I want to tell you today, or show you today, is experiments that we did with the scanning tunneling microscope, with the low temperature scanning tunneling microscope. And what we want to figure out in the measurements we do is details about how the magnetic moment or how the spin on molecules or magnetic atoms on surfaces interacts with the conduction electrons in the surface of our sample, and well, what we can learn from it and what we can use it for. So, hello. Come on. My notebook and this beamer don't seem to agree with each other, but I thought I had solved it. Yeah, did this a bunch of times on the coffee break and then settled on showing the image, and I thought it would be fine. Can I borrow a notebook from somebody that has the capability to display PowerPoint? This took 5 minutes in the coffee break, and if it takes 5 minutes again, that must be nice.
Maybe do you have another computer?
I'm sorry, I thought that my notebook would not find that it was not. Yeah, let's try. Perfect. Perfect. All right, so I apologize for the delay. Then let me speed this up. I'm probably telling you, the intro slides are probably telling you things that all of you already know. So I'll just be very quick about this. The thing is this: what we would like to study are spin properties or magnetic properties that show us quantum mechanical behavior, right? What often tries to prevent this is that the very electrons that we use to interact with the magnetic atoms will also scatter with the spin and take away the information or destroy coherence or entanglement. And so to depict this, I just chose basically two atoms. When you think about them, like the easiest way to think about this is to think of an antiferromagnetically coupled dimer. So say you have two spins here. They are coupled to each other either by some molecular linker or by some other mechanism. Then the ground state of this system in its isolation, right, would be a Heisenberg antiferromagnetic singlet state, which is an entangled state between the two spins of these atoms, right? Now, if I go to the other extreme and say I couple each individual atom very strongly to the substrate of my surface, right, then that is the dominant interaction to think about. And then predominantly, I will have individual magnetic atoms that are screened by the conduction electrons of the metal, and then the interaction between the atoms will be the secondary effect, right? And this will kind of scale, if you go into like a tight binding or hopping picture, This will scale with the ratio of the hopping rates of electrons between the atoms and hopping rate of electrons out of the substrate with the atom, right? And then doing electrical transport measurements, we cannot go all the way here because this will, in general, kill our ability to interrogate the atoms, right? In more detail, what would happen to such a system during a scattering process, like say you have the system coupled antiferromagnetically, right? The stable ground state would be a singlet state, so up, down, minus, down, up. And one of the excited triplet states would be up, down, plus, down, up, right? And if I excite the system from the ground state to the excited state, it's not coupled to any dissipative path, it will just stay there forever, right? The problem that we're facing, at least in scanning tunneling microscopy, and I guess so far as I see also in like break junction or electromigration devices, is that if a scattering electron comes about, to the best of our knowledge, or I should rather say over the past 10 years, all experiments we have conducted on molecules and structures that we have assembled can be fitted by saying that an electron out of the substrate does not scatter with the spin states of the entire object, it scatters locally on an atom. This is not proven at the moment, this is just all our experiments fit with what we observe. Well, what we also observe as a function of time is, right, if we, by the scattering, the system can randomly or stochastically switch between the excited state and the ground state. But the more severe thing is that if the electron scatters locally on an individual atom, then the states of the system that are left after the scattering events, the scattered states, are not anymore the idle states of the system. And this is a very efficient decoherence process that will in general hurt. So, what I want to tell you today is one or two things that, okay, let's say one thing in the beginning, where, jump over this is details, this is energy level renormalization by this scattering, so you not only lose, so there's a bunch of effects involved in this electron scattering. Lifetimes decrease, energy levels change by a renormalization factor. I want to show you now one thing where this is actually useful, where we can make use of this scattering. And then I want to show you, afterwards, I want to show you one way how we can probably avoid this. All right, so to show you where this is useful, I need to show you how we typically build molecules in my lab. We build them atom by atom on a surface of a copper crystal that we terminate with a nitrogen layer. So we make a atomically flat copper surface, then we deposit nitrogen atoms, let them anneal themselves, they self-assemble to a monolayer of copper nitride, and then on this layer we can place atoms. And this is an STM image of an individual iron atom that we positioned, that is there. And then we can go with our STM tip, fetch a second iron atom, position it next to it about a nanometer away, and we can go fetch another one and position it here. And then we have the small caterpillar of 3 iron atoms. And the atomic structure of this looks like this. So the overlay here, the blue and yellow dots, are the atoms of the surface, where the yellow ones are the copper atoms and the blue ones are the nitrogen atoms. And for this particular structure, you see that each individual iron atom gets grabbed by 2 nitrogen atoms. Okay, this is PowerPoint science, but if you do DFT, you can actually see this effect. So the nitrogen atoms form a polar covalent bond with the iron atoms and pull it into the surface, very strong. The displacement is over an angstrom. And this allows us to have reasonably strong super exchange interaction between these iron atoms. So you can make use of the kind of molecular nature of the surface to have super exchange that is strong, and that is, this is not the important part, that is stronger than the direct interaction with the electrons, right? This is different from, for example, just placing atoms directly on a metal surface. Then all you get is RKKY interaction that scales the same as the electron surface scattering. Okay. Close. We investigated this structure for a while, and to be conscious of the time, I don't want to show you how we arrived at this energy level diagram, but these are the low energy spin excitations or spin states of the system. We get 2 states that are two low energy states. If we apply an external magnetic field, these states show Zeeman splitting. Then there's an energy gap of about 7 milli-electron volt, and then come a bunch of higher excited spin states. These two states here are the Neal-like states. So these 3 iron atoms couple antiferromagnetically, meaning there's one state that is up, down, up, mostly, right? It goes like this in the magnetic field, and another state that is down, up, down, that goes like this in the magnetic field. And the interesting part is now that due to the symmetry, the twofold symmetry of the binding configuration, there's transverse anisotropy present in the system that mixes these two states when they cross, or when they want to cross. Right? So we get an avoided level crossing right around here, right here at 0 external magnetic field, or 0 magnetic field. And we can estimate this by fitting to a bunch of inelastic spin excitation spectra. We can estimate this gap here to be approximately 2 microelectron volts. And, well, now, since we have an avoided level crossing of a two-state system, one way you can make use of this is you can use this as a sensor, right? So you zoom into this a little bit. The idea for the sensing mechanism is the following, right? The transition matrix element between the excited state and the ground state will heavily depend on the amount of mixing of the spin states. So if I'm right here in the avoided level crossing, the transition matrix element is large for an electron scattering event. And if I move out by, for example, applying a magnetic field, the matrix element will decrease, and that means the lifetime of the excited state will go on, right? And this makes it such that we park, by bias field, park us somewhere here, the system now becomes very sensitive to any kind of magnetic perturbation, right? It is also sensitive, we know by now, to any other perturbation, for example, to strain or local environment changes, and those we think have mostly to do with something modulating the gap here. But what I want to show you today is the magnetic sensitivity. So we apply a magnetic field, and then, this I didn't want to show in the light of time, because this is the same thing I thought. It turns out, if we go through the math, that lifetime depends sort of linearly on the amount of magnetic field at the 3-atom structure. Right? We have figured out a way to measure this lifetime directly by going away from a DC STM measurement to a pulsed measurement. So we basically adopt some schemes from the pump probe community. We position a spin polarized tip, say, over this atom. Then we send in a short few nanosecond voltage pulse that will create a bunch of spin excitations in the system, and with a certain probability we will land in the first excited state, and then a time delayed probe pulse can measure basically how the system decays from the excited state to the ground state. We measure this by time delay magnetoresistance. And this particular structure and this particular environment had a characteristic decay constant of 5 microseconds. So that's the T1 time of this system, if you wish. Then the first thing you can do to characterize the magnetic sensitivity is just use this magnetic atom that you have here. So we like to make our STM tips spin polarized by simply picking up 1 or 2 or 3 magnetic atoms. It turns out that for this particular experiment, this was nice because this gives us a small magnetic moment. This is a paramagnet, so it's always kind of aligned. Well, it has some anisotropy, but to first order, it is always aligned with the external field. We can direct it. And by the virtue of having the STM chip over the structure, it is pretty close to this. And this allowed us, for example, to measure the exchange bias field between the last atom of the tip and one atom or each atom of the structure. This has been modeled and predicted theoretically. In this paper here, we are able to quantify this now because we can use the changes in the lifetime as a quantitative measurement, right? We can ramp the external field by a Tesla, see how much does the lifetime change, and go back, and then we can ramp the distance between the atoms to see how much distance do we need to change to get a Tesla effect. So this is actually a quantitative plot where we can say like movement of the tip and here on the y-axis we see the effective strength of the exchange interaction between the atoms. So this is this is the exchange bias field. And surprisingly, this is what actually surprised us a lot. At typical tunneling conditions, so something that you would normally choose in an STM, say 10 millivolts, 1 nanoamp or something, you're in this window here. So at normal tunneling conditions, the tip is already exerting an exchange field of over a Tesla strength. So if you want to do spin polarized SDM on molecules or small magnetic objects, this is something that you need to take into account. The tip must be very far away in order to not be sort of non-perturbative. Actually, it turns out for some measurements you cannot get the target. So going away from just sensing the tip, we can sense other objects. For example, here we assembled a stable or bistable antiferromagnet. This is 12 iron atoms. You can, well, in this beamer not very well, but you can see one atom appears a little bit brighter and this a little bit darker. This is a checkerboard pattern. This is in the yield state. In this size it is stable for minutes or hours if you wish. And then we place one of our 3-atom iron sensors here about 2 nanometers away. And then this guy can be switched between this yield state and that yield state. And what we now did is, when the system is one state or the other, we just position our tip here on this iron atom and measure the lifetime of the travel. And for each of the states of this big guy, we observe 2 distinct exponential decays. The lifetimes are different. They differ by about 26 nanoseconds. This is well measurable. Or you just use this to transduce into an amplitude by parking the measurement at a constant delay and just record the signal of the tunnel current as a function of time. And this gives us plots like this. So you see very clear 2-state switching in the amount of current we get over a time of, this is now minutes, right? And this 2-state switching is now the stochastic switching of this structure measured with the tip over this atom. So 3 nanometers away. And we're now going into other measurements that this enables. One is we can now actually remove the tip by several nanometers and still get information of our small magnetic objects. And that allows us to really get into a regime where we can perform non-perturbative measurements. The other thing we can do is, of course, now non-local measurements, right? Or remote measurements, if you wish. We can, next to one sensor, we can assemble multiple objects. And since all of these objects interact with this guy, we can measure all of them at the same time, right? So here's these 2 structures, both of them switch stochastically, and then the entire system has 4 states or 4 possible configurations, and those are exactly the 4 states we can then observe in the signal on the sensor. By this, for example, we can figure out that even though these guys are fairly far apart and they are antiferromagnets, they still interact with each other weakly. So, yes?
How does it switch? I mean, I didn't get that. You have a tip in the finder and then the other one switch from their own?
So, thanks for the question. I tried to brush over it. So one part is, when we raise the temperature a bit, it switches on its own. Okay. The other part is, while you're measuring here, you're injecting electrons into the surface. And these electrons can actually travel over quite long distances and then induce switching on these guys.
Despite the insulator?
Despite the insulator, despite several nanometers distance. Despite using, okay, here we didn't, but for other structures we can additionally use geometric frustration to limit the interaction, and it still is there. To be fully open with you guys, when we did this measurement, we did not know this. Like, we were under the impression our tip is a few nanometers away, we don't use too many tunneling electrons. After all, our bias voltage is only on for a few nanoseconds every few microseconds. So the duty cycle is very low. We're like, it'll be fine. Turns out it's not. You need to play a few additional tricks to really get into the regime to not perturb the switching. Which actually means that in the end, it took us quite a few years to ever see the intrinsic switching of such a structure. All right, yeah, at lunch, if you like, we can talk more about this. This was quite important. All right, the other thing that we learned from this, by seeing that even these structures here that are distant by about 4 nanometers or something, maybe 5, we don't know exactly the scale, that they still interact significantly. We were like, where the hell does all this interaction come from? And started to measure the interaction strength between our sensor structure and this 2x6 structure by basically placing it here, measuring the lifetime changes, extracting the interaction strength, then disassembling the structure and reassembling it again. measure the same thing, disassemble, reassemble, and in this way we were able to record this curve here. This is the interaction energy between the two structures as a function of distance. You can still see that even at 3 nanometers distance, there's still an interaction energy on the order of 25 micro eV. For comparison, we know the magnetic moment of the iron atoms. The blue line is the dipolar interaction between these structures. Okay, this was quite puzzling because, as Guillaume said, we have an insulating layer there. We're like, this should insulate everything. It turns out this copper nitride layer does not really. We teamed up with Angel Rubio's group, and Andrea Droghetti in San Sebastian did a bunch of large-scale VOPc calculations where this is a cross-section view, where he put an iron chain here, then a long line of copper nitride in between, and another iron chain. So these, he told me that over Christmas 2 years ago, these simulations occupied a large fraction of the Gaussian supercomputing cluster. The unit cell needs to be quite large, right? You need to account for the atomic unit cell and then also for the magnetic unit cell and all possible configurations of the spin chains. Anyway, so long story short, the simulations show us that, like an electron volt below the Fermi energy, there's a pretty distinct state living in the copper nitride. So this is basically evaluating the density of states here in the surface layer. And if you look closely, you see that here is another one. Here's another state that lives here, and this one overlaps with the Fermi energy. Right? So these are PD hybridized states between the nitrogen p orbitals and the copper d orbitals. And this guy is the binding state, and that guy is the antibinding state. The antibinding state overlaps with the Fermi energy and allows direct scattering of electrons. So an electron can scatter from the iron atom onto this state, propagate through, scatter on here, and go back. So this is like a sort of a long-range super exchange mechanism that is at play here. And this is, as far as we can measure, this mechanism is always antiferromagnetic for all distances, right? It does not oscillate in its sign here, and it is quite long-range. So this we found quite interesting. It was also the first application where the sensing structure that we have here told us something that we didn't know at all before. Okay, so see, my time is getting short. Still, we want to have spins that have a long coherence time, and these measurements that I just showed you told us that the copper nitride layer is not the way to go. So we thought, let's do something else. The thing that hurts the spin coherence of magnetic atoms or magnetic molecules on such surfaces is essentially the elastic electron scattering, right? Because you can engineer energy gaps or do some Zeeman splitting. The thing that is really strong and really hurts is elastic scattering of electrons. And we thought, let's just go to a superconductor, have a small gap at the Fermi energy, and this will sufficiently or should completely suppress the elastic electron scattering. To do this, we went back to, this is not invented by us, we just picked it up again as a nice substrate system. This is a silicon 111 substrate where we deposit, just 2 monolayers of lead on it. And the lead has the nice property that it diffuses into these islands that are tens of nanometers in lateral dimension and exactly 7 monolayers in height. And this is now such a tiny superconductor that it cannot screen the magnetic field completely, right? So it still has the energy gap of a superconductor. So here's a DI/dV spectrum, right? You see this energy gap of about 2 millieV around the Fermi energy. You don't see nice coherence peaks. This is another consequence of small superconductors, despite the way spectrum on this island. The nice part of this is these islands are so small that they stay superconducting up to magnetic fields of 5 Tesla. We can now place magnetic molecules on them, still keep our magnetic field control, but have them on a superconductor. The molecule that we chose for this was advertised and provided to us by Roberta Sessubi's group and Matteo Manini. It's a Vanadyl phthalocyanine, so flat phthalocyanine ligand, and then the VO sticks out a little bit, right? The oxygen points up, the binding is with the vanadium. The nice property of this guy is its electron spin is 1/2, and the electron spin resides in a single dxy orbital. And All right, time is running away. First thing to do is to figure out when you place such a molecule onto a conducting surface, does the spin survive, right? Or does some electron transfer happen that kills the spin? So we went to the Soleil synchrotron, deposited the monolayer of these molecules onto a lead crystal, and got XMCD spectra. They look very nice. They show us a magnetic contrast. We sweep the magnetic field. The XMCD signal matches exactly to a spin 1/2 with a G factor of 2. Okay? So that's nice. It looks like the spin is intact. With the STM in Stuttgart, we can look at these things in more detail. So here are 3 molecules. You see they look a bit different, right? One has a bright blob in the middle and the others are sort of flat. And we figured out, basically by statistics and looking at DFT calculations, there's 2 possibilities, right? Like the molecule is symmetric. It can either bind with the oxygen to the lead surface, or it can just lie there with the ligand and bind with the ligand. And interestingly, the absorption energies for both scenarios are about the same. And also in the STM experiment, we find about equal numbers of each. Really surprised us was when we took spectra. The one with the oxygen down looks like this. So you see 2 strong peaks around 0 volt, and then this gap here. This gap corresponds still to the gap of the superconductor, and these peaks are magnetic bound states, which I can tell you in a minute about. But the really surprising one was that the one with the oxygen up, the spectra we take on this molecule look exactly the same as the spectra of the island next to it. Shut up. 2 minutes. Okay, good. So these magnetic bound states come about by having to think a little bit further, right? So yes, we are now on a superconductor, and we don't have free electrons anymore, or single electrons at this Fermi energy, but we still have Cooper pairs. And the Cooper pairs can also scatter off of the spin, and if they do, they form a magnetic bound state. Theory for this is quite old, in fact, and has been developed by Shiba, for example, and Yu and Rusinov, and so those are the Yu-Shiba-Rusinov states. They are magnetic bound states in the gap that actually, in terms of spin covariance, just tell you this spin is, is interacting a lot with the superconductor. So the name of the game for isolation of molecules on a superconductor is get rid of those. And it seems that this oxygen up molecule here that we have does the trick. Right? It still looks intact. It should have its magnetic moment. There's no Shiba states, but so we looked at what could be the reason for this, and it turns out it is traceable to the symmetry of the dxy orbital. So the orbital where the spin sits in has absolutely almost no overlap to any orbital on the ligand, and it is also not overlapping with the states of the lead surface. So if you plot the spin density here, this is a plot by Federico Totti from Florence, you see the spin density is very nicely located on the ligand, and you see no spin density in the lead surface. So if you think, well, if this is symmetry, then symmetry breaking should break this, right? We tried this in DFT calculation. This looks like this. So we were thinking at first, all right, let's press down on it. This is stuff we can do with the STM tip. But just pressing down doesn't do anything in terms of spin overlap. So there's just basically no change in the spin, in the overlap on the exchange of the spin density. But if we tilt the Vanadyl out of the perpendicular plane, basically break the nice dxy symmetry of the system, then we quickly induce overlap of the electron wave functions, and then the spin spreads out into the lead. And this is what gives you the magnetic bound states. And just to make the story short, this is an experiment we can do in the STM. Right? You can press down on the molecule with the STM, and if the STM tip is one thing, it is non-symmetric, right? So it will always break all sorts of symmetries, and we can indeed see that for the molecules where the oxygen atom is pointing up, if we press down on them, we start with the free gap, and as we press more and more, we see Shiba states running into the gap. And the distance these states have from the gap tells you how strong the interaction is. And this lets us actually see in this full sequence that we can go from negligible or non-measurable coupling to weak coupling and actually go into the strong coupling regime where a Cooper pair breaks and the quasi-particle excitation localizes at the moment. All right, that's it. I would like to thank the entire team in Stuttgart that is working on these problems with me. I would like to thank you very much for your attention.